So it's a great honor for me to introduce the CFA colloquium speaker this afternoon, which is Professor Eric Herbst from the University of Virginia. Eric is the Commonwealth Professor, not in one, not in two, but in three separate departments: chemistry, physics, and astronomy. So I think that really speaks to, as we'll hear about in his talk, the importance of having breadth in trying to understand and predict the production of molecules in space. I've always admired Eric in the sense that it's always, as an astronomer, it's always easiest to destroy molecules. It's much harder actually to synthesize them. Eric got his PhD in, let's say, the 1960s.
No, not that bad. 1970s.
1970s, I'm sorry. Major faux pas. With Bill Klemper, this was obviously a very exciting time. This is when Exogen, or HCO+, was ultimately identified in space, and he and Bill really laid the groundwork for ion molecule reactions, which is a crucial beginning of molecular astrophysics. And he's continued really to be at the forefront of this effort for the many intervening years. So I'm very excited to hear more about his talk, which is Interstellar Chemistry Towards Large and Larger Molecules. Eric.
Well, thank you very much for that introduction. It's a great pleasure to be back here. And as you know, the title, of course, is written there. And what I mean by it is that I want to talk about current ideas on how the current, what astronomers call large molecules in interstellar space, are formed. And then the sort of last third will be on the topic of how we could observe still larger molecules by the techniques of radio astronomy. All right. First, a very introductory slide. This is, I guess, almost all the interstellar molecules that have been seen, not worrying about which type of evolutionary stage and star formation they're seen, or not in any star formation region at all. Anyway, there are about 200 molecules even now. That 2015 isn't the number of molecules, that's the year. So I guess I should change that too. Most of them are neutral. Some of them, though, are very exotic neutral species, and there are molecular ions as well, positively charged ones and negatively charged ones. And this does not include any isotopomers. So considering there are quite a few of those also, there are many more than the 200 molecules. The dominant elements in the interstellar medium, of course, are hydrogen and then carbon, nitrogen, and oxygen. And that essentially is a recipe for organic chemistry, if not biochemistry. And so not surprisingly, most of the molecules seen are organic in nature. I mean, they may be exotic, but they're not exotic in the sense that they don't contain carbon. So this is sometimes like the Earth, sometimes the molecules are quite different. Anyway, with mostly by rotational spectra, that means loosely defined radio astronomy, molecules have been seen up to 13 atoms in size, although I think the one with 13 atoms may have some problems. Okay. In addition to these molecules, then we have one other class of very large ones, and these are the fullerenes. So it's C60, C60 plus, and C70, and they are detected in the infrared, not in the radio. And then there are, of course, the PAHs, but they're not individual molecules. The PAHs, one can only tell that it's a class of molecules that resemble little bits of graphene, and they're certainly there, but they're not, as I said, they're not characterized as individual species. So in addition to the gas phase molecules, there are ice mantles, and in cold, dense regions, on dust particles, and the dominant molecule is water. These are not very exotic. The next dominant one is CO2 in dry ice, and CO and methanol, and there's some ammonia and some methane and a few other species. All right, now question of large astronomical molecules. Now, in the 2009 review article with Avina van der Hoek, we foolishly called any molecule with more than 6 atoms or more, which mostly meant 6 to 13 and still does, as complex organic molecules, which then got abbreviated as COMS. Now, when you give a talk to chemists, which I often do, and you call molecules of 6 atoms complex organic molecules, everyone laughs. So there's been an attempt to change it. And the first attempt was a bad attempt. It was done by a fellow astrochemist, and she decided to call them astronomically large molecules. Now, right, the problem, as I explained to her, and she's not a native English speaker, is when you use an adverb like astronomically, and it's modifying large and not molecules, and that means, very, very large. Astronomically, that's very, very large. So I think it's better to just call them large astronomical molecules, and as they get to being as big as the fullerenes, very large astronomical molecules. Anyway, so there are three classes of these molecules. First are the so-called carbon chains. These are molecules that are organic in nature, but they're very unusual by terrestrial standards. So they tend to be very linear. They tend to have these radicals and ions, negative and positively charged. And they tend to be very, very low, have very small amounts of hydrogen, which is very strange considering that hydrogen is the most abundant element by a long shot. Now, unlike the carbon chains, there are terrestrial-like ones. And these are the molecules, if you would go into an organic chemistry lab and smell the smell, these are the typical solvents that you find. That is, they're in the liquid state. They're poured around, and that's how you get the smell. But typically in space, occasionally seen as an ice, but most of the time seen in the gas. These alcohols, esters, other species, including a few with nitrogen, carbon, and oxygen. Now, then there are the fullerenes and the PAHs, which I'm calling very large astronomical molecules. There's clearly a sizable gap between the number of 13 atoms and the simplest fullerene seen, which is 60 atoms of carbon. And so there's certainly some gap to be filled by further observations. All right. I picked this out. This is the last time I tried to list all the interstellar molecules. I think it's about 5 to 10 years old. I don't even remember all the color codes, and they've changed anyway, it seems. But the molecules from 6 atoms to 13 atoms are the one I'm calling now large astronomical molecules, not very large. And they're mostly organic molecules, again, divided up into these carbon chains and these terrestrial species. Now, what has changed in 10 years? A lot of this has gotten filled up. Many new molecules seen between 6 and 13, but nothing greater than 13 other than the fullerenes. All right. What's the importance of large astronomical molecules to an audience of astronomers? Well, first of all, there's always the biological interest. The larger these molecules get, the more they get closer to simple species of importance in biology. And it would be very nice if we could really find one molecule that was definitely important. That's the simplest, that's the simplest amino acid, called glycine. And there's been a long and controversial history as to whether glycine has been detected or not. The other thing is it can help constrain the chemistry, because the bigger the molecule, the harder it is to make. And that means if we have a number of possible chemistries, we can try to understand which is the important one and which isn't from the bigger molecules rather than from the smaller ones. Now, if we understand the chemistries, it does help us understand the physical conditions and the timescales of evolutionary stages, for example, of star formation, because chemistry indeed is a function of pressure and temperature and lifetime. So it's very helpful, I think, for astronomy. Nowadays, though, with interferometry and ALMA, when we're seeing such complexity, we really have to understand these things very well, because the chemistry is likely to change on a very small scale, which we're not used to. All right, so here's, I showed this earlier, this simple picture of star formation. It looks complicated, but as people know about it, it leaves out a lot. So I'm going to talk about just large molecules, and eventually even larger ones. So the two regions that are going to be of most interest, at least at the start, are, this is in the low mass star formation evolution here, although the high mass has these regions too. a cold core, which is a place where you see these carbon chains. So the exotic chemistry occurs at 10 Kelvin and 10 to the fourth density per cubic centimeter. And the isothermal collapse starts, eventually becomes adiabatic, non-isothermal, heats up. And as one reaches a temperature, the gas that's now collapsing in on the protostar reaches a temperature of 100 Kelvin in the low mass system, and maybe higher temperatures called hot cores in the high mass system. That's where you start seeing the terrestrial-like molecules. So it was up until about 2 years ago, this was very simple. We looked at a chemistry that got us this at low temperatures, and we developed a chemistry that got this at high temperatures, assuming that they were mutually exclusive. Well, the theories are mutually exclusive, but the observations have now convinced us that life is much more complicated than this simple binary sample. And here's the reason. So let's look at these various classes of large molecules. The carbon chains, they are still found just in cold regions, to the best of my knowledge. Cold cores, as I showed you, infrared dark clouds, a high mass equivalent, and these pre-stellar cores that are still collapsing isothermally. That's okay. It's the terrestrial-like ones that are spreading out into other types of sources. So in addition to the hot ones, which we have a theory for, several of them, not a huge number, but several of the most important ones, have been found in these cold regions, for which they weren't found. Several others, towards the 6 atom, barely large molecules, are found in translucent clouds. Translucent clouds are in between diffuse clouds and dense clouds. And trying to understand how large molecules can be made in strong radiation fields is something we haven't yet figured out. And then finally, in protoplanetary disks, there are several what are called large molecules, both with 6 atoms. And that, we think we do have a theory that explains it, but I won't talk about it unless you want to ask a question. And I don't have time to talk about the fullerenes, but the last observation of a fullerene was in diffuse clouds. Now, it is hard to imagine a local production in a diffuse cloud with a very strong ultraviolet radiation field, a chemistry taking you up to C60 plus. So this may well be what's called a top-down chemistry, in that it may just be sputtering off of dust particles or something of that nature. But we don't really understand that yet either. All right, so here are mechanisms of how might the large astronomical molecules be formed. And this is somewhat historical, but has become mixed up now that there are different types of sources that have terrestrial-type molecules. Anyway, there are 2 low-temperature syntheses here. There's one that is used for the high mass and low mass warming up regions, and this has gas phase and grain syntheses. And then there are other possibilities, such as this top-down business. So first, I want to discuss the low temperature, the cold cores. So historically, the first models in the 70s, simulations, used the so-called ion molecule or ion neutral chemistry, reactions between ions and neutrals, because they're very well adapted to low temperature and low density. That has been added to by reactions involving neutral species, and I'll discuss why. And then we'll move on to what happens at low temperature grains. And if we're going to be looking for these large molecules in the gas, we're going to have to figure out how to get these molecules off the grains back into the gas. Okay, so low temperature production. The biggest problem we face now, and this is in the last 2 years, is that they can be found in these terrestrial-like molecules can be found in cold sources. And we're stuck with a theory that explains them in warm sources, but not in cold sources. All right, so simple chemistry here. This is a potential energy pathway, the lowest energy pathway from reactants to products. Just like, say nuclear physics, but many systems have barriers. So the barrier here is called an activation energy. And so a cross-section, chemists don't tend to use cross-sections, but a cross-section would then have a threshold of this activation energy, E sub A. chemists use rate coefficients, they're cross-sections times velocities thermalized, and you get this expression which has an exponent here. Activation energies in chemistry might be an electron volt or so, and if you have 10 Kelvin, I mean, this is not going to be much of a reaction, right? So now it turns out that the majority of reactions between neutral species do have barriers, and that was a problem to us. It still is a bit of a problem. There are exceptions involving one or two neutral species called radicals, which are odd numbered of electron species and which can be more reactive. But ion neutral systems have a bigger cross-section because they have strong long-range forces. So these are simple potentials. I mean, oftentimes, by the way, you just don't go downhill. There might be an intermediate well or something to make life more complicated. And the ions are mostly produced by the global mechanism is cosmic rays. All right, so here's an example, rather than doing a lot of organic chemistry. This example shows why ion molecule chemistry gives you exotic molecules. So we start with molecular hydrogen, which, as you probably know and will learn anyway, is produced on grains, not in the gas phase. But it's hit by cosmic rays, and the single ionization is one of the things that happens. You form secondary electrons, which also do ionization. H2 plus reacts with H2. There's much more hydrogen than the other elemental abundances of importance, the carbon, oxygen, and nitrogen, that 1 part in 10 to the 4th. Anyway, so within a day in a cold core, H2 plus reacts with H2 to make H3 plus, which has been detected in the infrared from the ground by Jabal and Oka. Now let's, since I want to consider water and something called hydroxyl, we have H3 plus reacting with oxygen, and this is what chemists would call a proton transfer reaction. It makes OH plus. OH plus doesn't live very long. It reacts with H2. It makes H2O plus, which doesn't live very long. Anyway, even though OH plus and H2O plus don't live very long, they still have been detected. As telescopes get better and better, even minor species get detected. Anyway, H3O plus stops it, and this a chemist would call saturated. This has all the hydrogens it could have. But when it comes apart with electrons, it makes the dominant species is OH. So this is what's called a radical, and it's low in hydrogen, whereas water, which is a normal species with more hydrogen, is only a 10% product. All right, so what does this show? It shows you that you produce ions, you produce radicals, which are exotic, you produce species that don't have much in the way of hydrogen. Now, you can do the same thing starting with carbon. So this is, instead of oxygen, CH plus is made. It starts reacting with hydrogen, but it doesn't react with the CH3 plus stops it. It doesn't go on to the so-called saturated form, CH5 plus. So CH3 plus, much of it comes apart by reaction with electrons. Some of it actually reacts with this very strange reaction called radiative association, which two species come together and stick by giving off a photon. That's actually been measured in the laboratory. But when the CH5 plus reacts with electrons, it makes CH3 as well as CH2 and CH, and very little of the standard CH4. So the net result, as you get to bigger and bigger molecules, is you get these very unsaturated linear species. So it's just what the doctor ordered. The neutral-neutral reactions are a little unclear what they do. We didn't worry about them until we had to. As I said before, most have these barriers. And even with barriers, at higher temperatures, they may become more important, but not at 10 Kelvin. But some don't have barriers. And then there's also the quantum mechanical problem of tunneling under barriers. Now, when we started doing this, chemists didn't think much about tunneling at low temperatures. It's become a big field, and there are reactions that are governed by tunneling. So we have to start worrying about that also. And the new research in the last few years shows that these neutral-neutral reactions may work at low temperature, and that's what may be making the terrestrial-like molecules seen in the cold regions. All right, so here is the strangest one of all. This came out in Nature a year to 2 years ago. Forget about what species are doing it, although it is important in space. So it's a radical and methanol. And this is a very strange looking potential, okay? So first it goes down, then it goes up, then it goes down again. And here's what happened. So they measured it at room temperature, and these are the products. And room temperature was pretty slow because it has a barrier. And then they measured it at higher temperatures, it got a little faster. Then they went to lower temperatures, and it also got faster, but really with a vengeance. So by the time they got down to 50 Kelvin, it was 2 orders of magnitude faster than at room temperature. Now, they thought about it, and they said, well, we have this new type of mechanism. The basic idea of having a well is that when the two reactants are in the well, or they're above the well, but still the dynamics are such that they move around and stick close together. Meanwhile, they can tunnel while the sticking together happens, and it happens faster and it happens more, complexes live longer and longer as the temperature goes down. There's more chance to tunnel. And that is their explanation, which they said was novel. Now, one of the problems of getting older, as I am doing, is that you publish things that people forget after 20 years. So actually, we had projected, this sort of thing is in the literature. And it was a paper in which I was a co-author, but it was 1991, and it was a different system. And then it was attacked as not being right, and now everyone agrees it is right. So in any case, it turns out to be very important because it's fast at low temperature and not at high temperature. So a group from Europe, Italy, and France used this reaction to use neutral-neutral reactions, none of which has a barrier, and many of which have just been studied by these groups, makes the two best-known terrestrial-like organic molecules in space. This one is dimethyl ether. That's not what puts you to sleep. That's called diethyl ether. I mean, this might put you to sleep permanently. I'm not sure, but in any case, it's dimethyl ether. Okay, right. And this one is methylformate, a class of molecules called an ester. All right. I don't really want to go into all these reactions. One that's interesting, because I'm not sure it's right, is one of these radiative association reactions in which two things just come together to make the dimethyl ether. Now, the group also said what this shows is, since the methylformate has to be made from dimethyl ether in this business, that means that you should expect them in the same place in space. See, nowadays with interferometry, we do have this spatial distribution problem. We have, if you find one molecule over here and one molecule over here, you can't have them reacting in a simulation. That doesn't happen. So you have to worry about this. So if this is right, they would say the prediction is you would find these in the same place and they're correlated. And they are. But I don't think that's necessarily right. I think what that means is you have a lot of one molecule and it makes a small amount of another, they're correlated. But suppose the first molecule disappears in making the second one. And now you look at it, they wouldn't appear to be correlated at all. So I think that problem of correlation hasn't been solved, but they certainly did make enough of these molecules. By the way, these are important because they have the most interstellar transitions, spectral lines. So they took a long time to be measured in the laboratory. And I was one of the people who helped to measure them, so it did take a long time. Anyway, CH3 is CH3. Oh, I want to mention, you have to assume this is 100% efficient. Normally, radiative association reactions aren't. So it's not clear to me that this is right. And we have to try to actually calculate the rates. All right. Now, methanol that started that sequence of reactions is actually formed on grain. So let's take a look at low-temperature surface processes. So we imagine an ideal surface. Think of, say, a tabletop that's flat. It's not really flat microscopically. Most of the time, they're regions, they're potential wells and potential barriers. And the best studied mechanism for surface chemistry is a diffusive mechanism, and it's named after Langmuir and Hinchelwood, two scientists, I guess, that worked on it. The idea is things will accrete, a species will accrete, and at low temperature they'll likely stick. But to react, they have to find one another, and that means going over barriers E sub B, either by hopping or by tunneling. So this is called a diffusive mechanism. It is the standard mechanism. Out of every, say, 100 surface reactions, I suspect 99 are thought to be diffusive. On the other hand, if maybe the temperature is too low or for other reasons one species can't move, then there's also a possibility that something from the gas can hit it. This is called an Ely-Rediel mechanism. Again, the names of two people. Okay. There are other mechanisms as well. Okay. Now, in the last 10 years, a lot of work has gone on, but surface science is a very hard subject, as people know. And there's still some uncertainties as to, for example, how important this Ely-Rediel mechanism might be. All right, some of the things that happen on surfaces, this has nothing to do with directly with large molecules. Hydrogen cannot be formed in the gas, except in the early universe it can by going through H- and H+, but not in the interstellar medium. So this is now a well-studied surface process. Two hydrogen atoms stick, and they are very weakly bound by what's called physisorption. They can move, and if they don't come off first, they can form molecular hydrogen. Association reactions on surfaces are fast because the grain can take the excess energy. So it's very efficient, and then it either comes off thermally, molecular hydrogen, because it's not bound strongly, or the actual energy of reaction can drive it off. So 10 to 20 Kelvin is a typical temperature range of which this occurs. This is grain temperature now, because less than 10 Kelvin, the hydrogen atoms are going to stop moving. And then you have to think of another mechanism. And above 20 Kelvin, they will accrete before they can react. So this is a perfect low temperature mechanism. There are also higher temperature mechanisms for making H2, which involves stronger binding of hydrogen atoms to the grain. All right, so here, generalizing to other systems, which have been studied as well, we're making two molecules here of importance. It's water and methanol. Water because it's water, and methanol because it's the largest ice seen. So and it is indeed made on a grain. But if we want to see it in the gas phase, it has to come off. Now, the reactions for water, H and O come together, and then another H and OH come together. At 10 Kelvin, it's mostly atoms that do the moving. The heavier molecules are bound too strongly to move. So methanol is formed, CO is formed in the gas, comes down to 4 hydrogen atoms react one after the other to give you methanol. It's actually been studied in the laboratory. And now how do we get some of these things off a grain? Now, molecular hydrogen, even at 10 Kelvin, can come off. These others, you need something non-thermal. It's not a thermal process. So we know there's photodesorption, there's reactive desorption, and a few other things have been suggested. Okay, so this is still in the process of being understood by better experiments. And now there's another possibility. There are other possibilities. I've been talking about diffusion. There's this Ely-Rediel mechanism. There are other mechanisms that surface scientists have thought. Now, can this make anything bigger than methanol? You know, in other words, start adding more hydrogens and oxygens? Maybe. The laboratory evidence is mixed. I mean, some of these things don't go, others do. This certainly needs this mechanism would need more experiments. Unfortunately, it gets, if you want to look for these in the ice, it gets harder and harder the more complicated the molecules get. The spectra, the infrared spectra, are rather broad on the ice, and it's not easy to see ices that are more and more complicated, and so there's less and less of them as against these things like water and methanol, which have stronger transitions. By the way, ices of up to 100 monolayers or even more can be formed if these cold cores last 1 million years or so. All right, in fact, here's a simulation of an old cold core of a grain I showed earlier. This is the grain, and here is some of the ice, which is simulated here by Monte Carlo methods to be rather amorphous, to have lots of holes in it, and the various colors of different molecules that are produced in our simulations. So imagine how complex the chemistry is if it's occurring on a surface. This is what a surface scientist would call a rough surface, which means it doesn't, it doesn't have one binding energy, and it doesn't have, anyway, it's a mess. And of course, reactions can also occur in the holes, in the bulk. So I'm not talking here about how we do simulations, but they're not easy. All right, now, here is what we do for warm regions. we have found that the best thing to do is to actually have the chemistry occur as warm-up is occurring. So this is now, you're thinking of protostellar regions and stuff is coming in and warming up. And the chemistry is occurring during the warm-up. That seems to be the most efficient way of doing it for the following reason. So we're starting with a cold cloud here, and eventually the system becomes adiabatic and starts to heat up. Okay. During the cold phase, remember, we have the ion molecule reactions, the neutral-neutral reactions, the stuff on the surface, and ice chemistries all occurring, and some complex molecules, some large astronomical molecules being formed. All right, but what happens now with the warm-up is this seems to be a perfect way of making large numbers of different ones, not just the two large molecules produced by that neutral-neutral system. So here's what happens. As the temperature goes up, atoms do not become very important because they can't stick long enough. They go away. Meanwhile, the bigger molecules, say the methanol and other things, start to move. Because moving is easier than getting it off. But they're not reactive, most of these species. So how do they react? Well, there are various ways of making them reactive by knocking off atoms or so. And in this model, which we did a decade ago now, it was done by photons. Now, even in dark, dense clouds, there are photons caused by cosmic rays. And the photons, we know the cross-sections in the gas phase. So we thought, well, we make an astronomical assumption here that the cross-sections for photodissociation into radicals in the gas phase is the same as on an ice. Of the 2 or 3 examples, I know it's not true, but it's not bad. And the other possibility would be cosmic rays doing it directly, forming high-energy secondary electrons, forming low-energy secondary electrons. We're trying to understand that. It's very, very complicated. So we don't have a full theory. Anyway, once you form these radicals, and I'll give an example on the next slide, they can come together and form all these terrestrial-type organic molecules. So this is a general theory of forming makes lots of predictions of large ones and larger ones, as long as people could find them. So far hasn't been the case for many of them. All right, G doesn't stand for gas, it stands for grain. I wanted to use an I for ice, but that sounds like an Apple project. So G. My graduate students like to put J here, but that's just totally confusing. In any case, so these are surface. These are molecules, say, towards the top of that structure I showed, trying to make their way around and come together. And these reactions, this is now a methylformate and dimethyl ether. So just to show you, you can do the same thing on grains as you can with neutral reactions in the gas, probably much more efficiently here. And a former colleague at Virginia actually studied some of what they call recombination reactions. And they do seem to go, they're not the only process that happens in surface chemistry, but they are much more prevalent than they are in the gas, these sticking reactions. And Karen and other people have actually studied this sort of thing, but it's very hard in surface chemistry to study individual reactions, not like the gas. So if you say you shine radiation on an ice, or something resembling an interstellar mixture of ices, and you find you make complex molecules, it's not one reaction. And the only way to understand this is to simulate it the way we would simulate an interstellar grain growing ices. And this is a hard thing to do and hasn't been completely done. If you don't believe in the photon mechanism for making these radicals, then there is direct cosmic ray bombardment as well, which may be comparable, which we haven't yet worked out. All right, then now, about 2 weeks before coming here to give this talk, I learned of a new mechanism that has been suggested. This could work at a variety of temperatures. And this comes, the first authors, Vianney Take, comes from Chaudley's group at NASA Goddard. And this is now, you can look at this as a, let's go back. You can look at this as a if you wish, as a non-thermal desorption, a new desorption mechanism that's macroscopic rather than microscopic. And I also wrote in here, by the way, that there's also a warm gas phase chemistry. So gas phase chemistry can make some of these molecules at higher temperatures also. So it's getting rather complicated. But anyway, luminosity outbursts. I'm not an expert on luminosity outbursts, but these things do happen in stellar formation regions. And either by the photons or by rising in temperature, they can drive molecules off of grade. So it is a non-thermal desorption mechanism. I don't know if that's how the authors looked at it, but and so that puts methanol, ammonia, and other species out of the ice into the gas phase, ready to react. Now, considering they have methanol, you would think they would use those neutral reactions that the other group did, but they seem not to have heard of them or want to ignore them. So they have another series of reactions. They use ion molecule reactions to make the methyl formate and dimethyl ether via their protonated precursors. Now that I thought, when I saw that, I thought that's impossible, because the dissociative recombination reactions with electrons first never just lead to a simple one hydrogen coming off, but fragmented, or hardly ever. But they thought of that in a very clever way. They've avoided the destruction mechanism of dissociative recombination reactions by simple charge transfer with ammonia. Now, it turns out these reactions are very exothermic, so the protons always go to ammonia to make what a chemist would call an ammonium ion. And so instead of destroying the ion, you convert it into the neutral. Okay? And they claim there's more ammonia than electrons, and I'm not so sure. As I said, I've just seen this, but this has made ion molecule reactions more efficient also in making large molecules, if it's right. And so they made an extreme statement that you don't need the grains for anything, but clearly they started with stuff on grade, so that seems unfair. And, so anyway, you can see what's happening. If you concentrate on methyl formate and dimethyl ether, it's going to be very difficult to decide which is going on, what process is going on. If you want a theory that produces lots of these terrestrial-like organic molecules, then still the grain theory of warming grain seems to be the only thing that we have. If you like pretty pictures, which tell you very little, I thought this was a nice one. This came from the Faraday Society is a British society for physical chemistry, and they've become interested in astrochemistry. So this was a meeting put in some journal called the Faraday Discussions, Astrochemistry of Dust, Ice, and Gas. And this either graced its cover or something inside the cover, I don't remember. But it's very complicated thing, and it would take almost a whole hour to explain all these processes. And it doesn't really have them right anyway. It has molecular hydrogen being formed after an ice forms, and most of the hydrogen forms on the plain silicate or carbonaceous grain long before ice is formed, because molecular hydrogen is even formed in diffuse clouds. It's very efficient. Anyway, it has things like, I assume this means cosmic rays coming in. It has chemical reactions. It has photodesorption, radiation of various sources. Anyway, I guess it has most of the processes in here, but it's just a picture. So I thought we'd make an equally complicated picture. What this one shows, which I don't want to go into detail, is that we, faced with all these new mechanisms for forming large molecules, we would have to put them into a model. So this is a model that we're going to try to explain all interstellar sources, all evolutionary stages. It's going to work between 10 and 800 Kelvin or so, we hope. And it's even going to work at high-density regions of protoplanetary disks near stars with so-called three-body reactions in the gas. It has grain chemistry, gas chemistry, all sorts of things. It's still in progress. Maybe a long progress, a slow progress. Anyway. Okay, so the second, the shorter part of the talk is, how can we see larger molecules? And then seen up to now. So we'll call anything with more than 13 atoms, so very large astronomical molecules. Okay. And they are poorly constrained chemically. And I say poorly observed, but other than the Fullerenes, they're not observed at all. So I guess that's poorly, but very poorly, but in any case. All right. So can radio astronomy help? So we were having a meeting on radio astronomy and new things to do with it. So that's where this slide first appeared. Difficulties. I'm not sure the difficulties are difficulties, so let's go over them. Large partition functions. What this means is that as molecules get bigger in size, they have bigger moments of inertia, and that means the rotational levels are closer together. So if you're looking at one transition, there's going to be less intensity in individual transitions. You'll have more of them, but they'll each have lower intensity, and that's going to be hard. That's assuming thermal equilibrium, though. Suppose a rotation is relaxed. Then you might have much of the intensity in the lower lying levels. So this is not obvious to me. Lower abundances. Well, it's certainly true. If you extrapolate our theories, the more complicated the molecule, the lower the abundance. Okay. On the other hand, for all we know, it can suddenly curve around and become more abundant. Like C60 plus in diffuse clouds just boggles me. We have to keep an open mind on this sort of thing. More laboratory work needed. I think there's a lot of laboratory work that's been done on these terrestrial type as well as the carbon chain molecules. This trend towards lower frequencies, that's true. Well, with all the work, radio work tending to go now to higher frequencies, there may be a role for lower frequencies. So let's take a look at that. These are some examples of very large molecules, although these aren't so large. But R in chemistry means some combination of carbon and hydrogen, like methyl and ethyl and all these things. This is an amino acid, by the way. If you're wondering what this has to do with the structure, whenever you see parentheses nowadays, it means it's going off on a different shade. So this is anyway, chemistry shorthand. All right, so let's take a look at frequency. So I've cheated to make this the lowest frequency possible. First of all, I'm going to choose a linear molecule, and we're going to do it in the emission, LTE. And this is now the transition of maximum intensity. It's not the maximum frequency, it's the frequency of maximum intensity. So this is where it peaks. And it goes as the temperature to the 1/2. B is called a rotational constant, and it's sort of 1 over the moment of inertia. For a linear molecule, there's only 1 moment of inertia, and in appropriate units. All right, so this is correct. The square root of 3 is confusing, but that has to do with the fact that it's rotational. So you have to worry about emission and absorption and all sorts of. It's more complicated. So that gives you a factor of 2 or so, which doesn't really matter. So this formula, I think is right. And I've seen it in textbooks also. So what I'm now going to do is say every linear molecule is just carbon atoms. We'll forget about anything else. And that's a pretty good approximation. And this is a standard bond distance. Chemists have now decided to use picometers. It's gone from angstroms to nanometers to picometers. So in any case, so this is what's called a double bond. But in any case, and I'm going to choose a temperature of 10 Kelvin. So I'm really weighting it towards low frequencies. So if you have 5 atoms, 5 heavy atoms, like 4 carbons, say, and a nitrogen, this is the maximum. The peak is at 54 gigahertz. I've checked this for some of the cyanopolyines. It sort of works. Anyway, by 20, you're down to 6.7 gigahertz. So that means that you're going to have to, you want to think in terms of lower frequencies. Now, that is exaggerated for many reasons. First of all, you don't have to have a source of 10 Kelvin. Secondly, nonlinear species don't have as strong an effect. We've run these also. They will go to lower frequencies, but this nonlinearity will push the frequency range higher. There are 3 rotational constants involved. All right, so what do you want to do? I suspect you want to work on, say 1 to 50 gigahertz would be a reasonable place to look. And this means that although the square kilometer array sounds like a good idea, you probably need more than that, okay, to get up to more than 10 gigahertz. Any case, so what do you need? You need a large collecting area to work at low frequencies. It's not that efficient. You want either very good spectral resolution, or velocity resolution, or spatial resolution. Otherwise, low frequency spectra, at least the ones I've seen, tend to be very complicated. So there's a large paper in the monthly notices, 2015, Cormier et al. It's an NRAO project to actually look at Sagittarius B2 at low frequencies. Now they look at 10 to 15 gigahertz, okay, and it's now been done with interferometry with the Australian Australian compact array, and they're starting to use the VLA, and it's very, very complicated. For Sagittarius B2 is a hard thing. You have emission, and right next to it you have absorption with a slightly different velocity component. You have shells around the sources of continuum emission. You have along the line of sight, you have lots of clouds in addition. And this is the source in which there are translucent clouds along the line of sight, which they claim they're seeing large, well, 6-atom, 7-atom, large astronomical molecules, which I don't yet understand. We're having to try very exotic methods to try to see if we can reproduce that. But closer in, there are shells that have even large molecules. So this is an interesting paper if you want to see the complications of what can be done at low frequencies for large molecules. But since the square kilometer array is not the best, is not the only thing, this was trying to propose that people fund the expanded VLA. Now, much of this I think you understand better than I do, but the key numbers are 1 to 50 gigahertz, so it sounds like a very good thing for looking for complex molecules. We would have to be lucky, but look what happened to the gravitational waves. So it's possible. Future, okay, synthesis of large molecules. Well, I say we're going to try to find out which mechanisms are important under which conditions. It's become very complicated. It might be that interferometry will help us because we'll have very specific regions with very specific molecules, and maybe, we'll see. And we may be able to extend this to the very large astronomical molecules. Observations of these large ones will, I think, tend to go towards lower frequencies. Not only large collecting area and either interferometry or very good velocity separation. And the square kilometer array and the extended VLA would be the sort of the telescopes to use. And my acknowledgement, since I've been around now a while, I have both recent group members and progeny. So progeny is more than, 10 years ago, or something like that. Okay, and sources of funding. And thank you for your attention.
Do we have questions?
Yeah, I have a question about the desorption mechanism. So
Yeah.
you said there was thermal and non-thermal desorption.
Exactly.
Grains. So imagine as the grain heats up,
Yeah.
the lighter molecules will move faster and they can't meet.
And yes, they first move faster, and then as the temperature heats up more, they come off.
Yeah, because basically they can't be held onto the grain.
That's
So
exactly right.
in the non-thermal desorption, that involves a photon being absorbed?
That involves a variety of mechanisms. I mean, I would call this a microscopic mechanism. Yes, a photon, like a photoelectric effect. It's a photomolecular effect. But it's much more complicated. So the first molecule that was studied was carbon monoxide. And carbon monoxide, the spectrum, if you take it as a spectrum, you use different frequencies of photons, you get a spectrum that looks a lot like the electronic spectrum of gas phase CO. Broadened, but okay.
Not in solid phase? Or?
Yes, it looks like the solid phase photodesorption spectrum looks like the gas phase. What does that mean, I guess, is that the first thing that's happening is a CO is on the surface is excited into an electronic state. It's a singlet pi electronic state. And then some of that energy gets converted into something that kicks it off. Methanol, water, continuous, not discrete. And both of those have continuous gas phase spectra also.
So typically what fractions of CO, for example, would be thermally desorbed as opposed to non-thermally desorbed?
Well, it depends on the system. If it's at 10 Kelvin, it has to be non-thermally desorbed. If the system heats up to say 300 Kelvin, you're going to lose the ice mantle completely. I should have said that. Yeah, everything will be desorbed. You'll be back to bare grains. And then you might have a high temperature chemistry with stronger binding. That's another possibility.
And for the really big molecules that you form on the grains.
Yes.
If you do a non-thermal desorption, which I think you'd have to do, can that destroy the molecule, or does it break it apart?
This has been a controversy in literature for a long time, and the most recent papers I've seen, and that people in the audience who know more than I do have dissociation of methanol, for example. So it is a dissociation, not a simple. And there's other evidence for the opposite.
I'm a little pessimistic about getting something significantly bigger than the square kilometer array.
I didn't say bigger, I said operating at higher frequencies.
Well, I just want to point out that with the square kilometer array, that you can do a kind of experiment for this that hasn't been done before, which is to look in absorption against quasars, say, right? And in the square kilometer array, quasars are going to be very bright, and to the extent to which they're behind the clouds you're interested in, you don't have to excite these things into any kind of emission in order to see them.
Right, that's right.
So SKA will do a very good job.
Okay,
of that.
sorry. What I meant is I was sort of taking back my extreme calculation that only had the lowest temperature and these linear molecules, and that really throws it under 10 gigahertz once you get to about 15 atoms. So, yeah. But there are arguments to both directions. Yeah.
I was wondering what work has been done on glycine to see how it's made and what likely would happen in space with low temperature conditions, grains, and so forth.
Right.
Has there been much work done on
There's first of all, getting the spectrum was very hard. Glycine is normally found in water solutions, and so it had to be. I guess it was something like electrospray was the first experiment. How did they get it?
I think it was glacier that they.
Anyway, so that was hard. As far as what conditions it's in, and there are mechanisms, theoretical, there are papers claiming it could be made with this warming up grain surface mechanism I mentioned. I haven't done it, but it was done by other people, and they claim it. And then you have to get it off intact, which you probably could do if it were just done thermally. But the controversy is whether you see it or not. And this is very difficult. There's some sources that are so rich in molecules that there's very little space for new ones. And something big like glycine, unless it's very surprisingly abundant, it's very hard to tell. Even if it is there, it will just be blended with other lines. That was the negative argument. The positive argument was a group claimed that they're now claiming, but they're not publishing it anymore, that they found glycine lines where there was nothing else. I've heard that in talks, but I don't.
The last I knew, that was just the stuff about 10, 20 years ago.
Yeah, that's right. That was when I was a scientific editor of the Astrophysical Journal. I almost got sued over that. So, I wasn't sure whether it should be posted on, so I sent it to my toughest referee. Now, figuring he'd find everything like this wonderful. So he comes back with a report saying, I've been too tough. I think this should be published because it would be good for the community to argue about this. Anyway, so then anyway, it's a complicated story, but lawsuits were threatened.
So some of the molecules that people have been batting around with theory has been non-polar molecules, which have their own associated difficulties with.
You need it. Yes, well, non-polar molecules can have weak rotational transitions, like molecular hydrogen, for example. But if you want to look for strong lines, you do have to look for infrared. So H3+ is an example of seeing it in the infrared from the ground, which is amazing. But it's lucky. It's right in a region where infrared penetrates the atmosphere. It's the atmosphere that's the big problem in the infrared. So new telescopes should help that. And other molecules have been seen in the infrared. So gas phase ones and surface ones. So which one are you thinking of?
Like specifically or just classes?
Large ones?
The large ones that have been proposed for diffuse interstellar bands.
The diffuse interstellar
Yeah.
bands. So some of the large ones would not. Okay. Now, the diffuse interstellar bands are electronic transitions. Okay, electronic transitions do not require a dipole. The transition dipole is not the same as the permanent dipole. It's a psi2 used to operate a psi1. Only for rotational ones can you make the assumption that the transition dipole is pretty much the same as the permanent dipole. We can go over that. You can look it up in the spectroscopy book, or I can show it to you.
Yeah, so I'm wondering for pHs, because they seem pretty abundant, do we expect transitions more in a megahertz regime, for example?
Well, I think people in the audience have actually looked. No, if they're big, yes. But there are small ones which we'll look for, which were not found. Now, the other thing is the polarity. So they're tailor-made for the infrared. Now, the problem with the infrared and big molecules is they don't really tell you structure. You see, rotational spectroscopy tells you moments of inertia, which, with enough isotopes, gives you the actual structure. Infrared tells you things about the molecule. So, for example, the infrared bands that define the PAHs can come from smaller molecules or bigger molecules, or molecules that aren't completely PAHs but have nitrogen atom. It's very hard to determine the exact molecules. So the best, I think, that's been done over many years with different spectra is to get some sense of the size distribution and that these are PAHs. But getting individual molecules may be impossible. It certainly has been up to now.
But you showed that by the spectra, basically you did this calculation with this 4 carbon atom thing. If you make them larger, I imagine the transitions go lower and lower in frequency.
That's correct.
But you think these are...
By 20 atoms was...
Yeah.
Oh, I did linear ones only because it was a simple thing to explain to an audience. I mean, certainly we could do the same type of calculation for any structure, just make things bigger with more atoms. You will get the same effect, but you won't get... It's not 100%. You will have, there'll still be there will be higher frequency transitions.
So the last question is Nimesh.
Your talk was about interstellar chemistry, but I was wondering if you can comment also on circumstellar chemistry.
On circum?
Yeah. So,
okay.
there are many
Circumstellar chemistry also has its confusions, So what molecules have been used the most is to look for older stars with extended atmospheres. Right? The carbon-rich ones are very rich in organic molecules. The oxygen-rich ones are now also surprisingly rich in organic molecules. And I have run models in collaboration with others on carbon-rich chemistry. The carbon-rich chemistry is more neutral than it is ion molecule. It may have changed, but I don't think an ion has been seen in the carbon-rich. Has HCl plus been seen?
HCl plus.
It has been seen, but it's pretty weak.
It's pretty weak.
Yeah. So there are differences.
It does, the circumstellar envelope, it does lend itself to observe with interferometers.
Mm-hmm.
It does have some sort of approximate spherical symmetry, but
Yeah, we have done models on that.
Yeah.
I mean, it's not all star formation. So one of the things I've also done in an ALMA project is AGNs, which we talked about before. And things, talking about things being protected, there seem to be molecules right up against black holes. So they're protected.
All right, we should end. So let's thank Eric again for very much.